You ever stop and think about how a database with petabytes of information, that's millions of gigabytes by the way, can find one tiny little thing in like the blink of an eye? I mean, it just shouldn't work, right? It feels like it defies the laws of physics. Because deep down, inside every computer, there's this huge speed gap. A gap between how fast we can think about something and how fast we can actually go and get it from storage. And that gap should just slow everything down to a crawl.
All right, check this out. It's kind of like this. Imagine getting data from a spinning disk drive, or even a super fast SSD. It's like you're in New York, you decide you need a book, and you have to fly all the way to Los Angeles just to pick it up from a library. It's a whole trip, but getting that same data from your computer's memory, that's like the book is sitting right on your desk, you just reach out and grab it. So the difference isn't just big, it's absolutely colossal. And since most of a database's data lives on that slow cross-country trip storage, how on earth do massive databases feel so fast? How do they pull off this magic trick, this illusion that everything is right there on your desk ready to go in an instant? Well, it's not actually magic. It's one of the most brilliant, most fundamental pieces of database design. It's this invisible engine that makes our entire fast-paced digital world even possible.
So let's pull back the curtain and meet the component that bridges this massive divide. It's called the Buffer Pool Manager. And you can really think of it as the ultimate gatekeeper, standing right between the slow, sprawling world of the disk and the lightning-fast world of the CPU.
So check this out. When the database's brain, that's the execution engine, needs a chunk of data, it doesn't go on that long trip to the disk. Nowhere. Instead, it just asks the buffer pool. And you can see here, the buffer pool's whole job is to be smart about this. It tries to predict what the execution engine will need and keep the most important chunks of data, which databases call pages, kind of like a page in a book, ready and waiting in that super fast memory.
So what is the buffer pool, really? Well, it's just a big chunk of your computer's memory that's set aside to act as a cache. It's organized as this array of fixed-size slots called frames, and each frame is perfectly sized to hold one single page of data from the disk. And by managing this cache really cleverly, it makes the entire enormous database feel like it's running completely in memory, even when it's way too big to actually fit.
Okay, so when the database asks for a page, the request can go down one of two very different paths. Let's actually follow a single request and see how this all works in practice.
First up, we've got the happy path. This is what we want. It's called a cache hit. The execution engine asks for a page and boom, the Buffer Pool Manager checks its records and it's already there, sitting in one of its frames in memory. Access is pretty much instantaneous. This is the goal right here. But what happens if it's not there? Well, that's when we take the scenic route, also known as a cache miss. The page that we need is way out on that slow disk. And now, the Buffer Pool Manager really has to earn its keep and do something a lot more complicated.
So here's the play-by-play for a cache miss. First, the manager looks for an empty frame in the pool. Simple enough. But what if there are no empty frames? Well, then it has to make a really tough choice. Which page that's already in memory gets kicked out to make room? We'll circle back to that in a minute because it's super important. For now, once it has a free frame, it copies the page it needs from the slow disk into that empty spot. And finally, it updates its internal map and just hands the execution engine a pointer to the data's new home in memory.
So how does it keep track of all this stuff moving around? With this absolutely critical data structure, the page table. Seriously, just think of it like an old-school library's card catalog. It maps the permanent address of a page on the disk to its temporary, in-memory address inside one of those buffer pool frames. It is the single source of truth for what's in memory and exactly where to find it. But the page table does more than just track locations. As you can see here, it keeps tabs on a couple of other really vital pieces of information. First, there's a dirty flag. This gets switched to true if a page has been changed or modified. That's a signal to the manager, telling it, hey, you have to write me back to the disk before you kick me out. Then there's the pin counter. This tracks how many different threads or processes are using a page right now. A page can't be evicted if its pin count is anything other than 0. I mean, that would be like a librarian ripping a book right out of your hands while you're in the middle of a chapter. Can't have that.
And that brings us to maybe the toughest decision the Buffer Pool Manager has to make. The pool is totally full, a new page needs to come in from the disk, but wait, nothing can be kicked out if it's currently pinned. So assuming it finds some pages that aren't pinned, it now has to decide which one gets the boot.
And this right here is the whole game. A good decision means you're keeping the data used a lot in memory, and performance is amazing. But a bad decision?
That means you're constantly going back to the disk to get stuff, which is a terrible state called thrashing, and your performance just grinds to a halt.
So how does it choose? Well, it uses something called a buffer replacement policy. A classic one is least recently used, or just LRU. The logic is super simple. You kick out the page you haven't touched in the longest time. It's like cleaning your desk by getting rid of the book you haven't opened in 6 months. But, tracking the exact timestamp for every single page access can get really expensive for the CPU. So databases often use this really clever shortcut called the clock algorithm.
Okay, let's walk through this, because it's pretty cool. Imagine all the frames in the buffer pool are arranged in a circle, just like a clock face. Now, each frame has a single reference bit. Just think of it like a little sticky note. When a page gets used, we put a sticky note on it by setting its bit to 1. Simple. Now, when we need to kick a page out, a clock hand starts sweeping around the circle. If it lands on a page that has a sticky note, a bit set to 1, that page gets a second chance. We just take the sticky note off, flipping its bit back to 0, and the clock hand moves to the next one. But if that hand lands on a page with no sticky note, a bit of 0, that's our victim. That's the one that gets evicted. It's just a beautifully simple and super efficient way to get pretty close to LRU without all the overhead. All right, so at this point you might be thinking, hold on a second. My operating system, Windows, Mac OS, Linux, already does this, right? It caches files from the disk in memory. So why do databases go through all this trouble to basically reinvent the wheel? And that is an excellent question. The answer really gets to the very heart of what makes a database so special.
The biggest reason it all comes down to is control. For instance, a database needs to guarantee that a whole series of operations, what we call a transaction, either all succeed or all fail together. The OS, it has no idea what a transaction is. It might just write a modified page to disk at exactly the wrong moment and completely corrupt your data. A database's buffer pool, though, it understands the transaction. It can manage those writes with surgical precision. It can also be way smarter about something called prefetching, loading pages into memory before they're even asked for, because it can look at the query plan and see what's coming next. It's a level of intelligence that a generic OS just can't possibly have.
And all of this leads to a famous saying in the database world from Professor Andy Pavlo at Carnegie Mellon: the operating system is not your friend. When you're building a truly high-performance database, you just can't rely on the OS to do the right thing for you. The philosophy has to be you manage your own memory, period. So, why does all this nerdy, low-level detail matter so much? Because this right here, this is the invisible engine that makes our modern digital world even possible. Let's just look at one of the most demanding data systems ever built, Google's Bigtable.
We're not talking gigabytes or terabytes. We are talking about petabytes of data. That's a 1 with 15 zeros after it. Millions and millions of gigabytes. This is a system designed from the ground up to handle an amount of information that's just hard to even comprehend, spread across thousands of machines where every single millisecond of performance counts.
And this isn't some research project locked away in a lab. Bigtable is the storage system behind stuff you probably use every single day. Things like web indexing, Google Analytics, all the satellite imagery in Google Earth, and personalized search. That seamless, instantaneous speed you experience when you use these products, that is a direct result of these fundamental data management techniques, all working at a truly planetary scale.
And that really is the core of it all. Underneath all the smooth, simple interfaces of our digital lives, there are these unbelievably complex, highly optimized engines like the Buffer Pool Manager, just quietly defying the physical limits of our hardware. It kind of makes you wonder, what other invisible engines are out there powering our world, making the impossible seem possible every single second?